Lab 6. The integration of all the experiences in this course, from circuitry craftsmanship, to experimental skills, to the mastery of knowledge in circuit and signal analysis. It is the culmination, or, figuratively, the crown jewel project of this course. The approach is to start with the quote-unquote big picture first. Why do we learn circuits and electronics? What is it for? Surely, the obvious answer is that electronics is useful. This Lab 6 is designed for us to appreciate one of the most essential use of electronics. Unlike other previous labs, in which we start by looking at the trees, here, we start by seeing the forest first. By seeing the whole plan, we will understand later and appreciate the circuits that we will learn and build. Let's begin. Can you live without the internet? What is the single most feature of the internet that makes it so special in modern time? Information. Sure. But information is not new. Humans have generated information and archived them in media from rock, clay, to animal bones, and eventually to papers for thousands of years. Imagine, you can take a picture of your dinner with the fanciest camera of the latest smartphone, but you can't post on any social media for your friends and family to see, because something is down. The worldwide telecommunication system is down. There is bountiful information generated every second by billions of people. But the information has nowhere to go, to be shared, because there is no telecommunication. No information can be sent to and retrieved from data centers. The internet as we know it would cease to exist. Thus, the essence of the internet technology is communications. In this Lab 6, we will see in a most simplistic way possible, how circuits and electronics are used for communications. Let's start the whole story of Lab 6 with the theme of communications. Suppose we want to send this message. It consists 14 bits, 1 and 0, representing two ASCII characters, H and I, or hi, for greetings. For the sake of simplicity, we will not use any realistic transmission coding scheme, but represent the message with a simple two-level voltage modulation scheme. A pulse with non-zero voltage for bit 1, and a pulse with zero voltage, that is, no pulse, for bit 0 as illustrated. All is nice and well if that is all there is to it. However, the physical communications process is not that clean. Suppose we have a voice conversation with someone. The signal of our voice is transmitted in the form of air pressure vibration in the range from 20 Hz to 20 kHz, which is the frequency response range of human hearing. But can we have a perfect, error-free, vocal communication in a noisy environment? Such as in a stadium, or a theater, or a crowded public place, where the crowd make loud vocal sounds. This is a case of interference. Other similar communications interfere with the one of interest. Even in a place without such interference, there can be other sounds, man-made such as engines, machines, or just natural such as wind blowing, wave crashing that also generate air pressure waves that interfere with the vocal communication of interest. There are the same issues in real-life communication technology. The path of information flow from one point in the world to another, is littered with noises and interference that tag along the flow. Without these problems, there would not be much about communication engineering and technology. And we would not have topics to talk about this Lab 6. Hence, we will introduce noise and interference to the simulated signal. In order to add noises and interferences, however, we need a little circuit. This is an adder. It adds two input signals into a single output. Perhaps one of the simplest applications of the op-amp. In fact, before the days of digital signal processing, this was how audio tracks, including karaoke, were added. As an example, in the follow, two tones will be added, and we can listen. This is the first tone, 1174.7 Hz. A musical tone. Although what you hear rendered by the DG-Lent AD2 audio function might not accurate, the idea is the difference in the frequency that we can recognize. This is the second tone, 1760 Hz. Both tones are added together. The following is a demonstration of beat, a phenomenon when two harmonics of very close frequencies are added together. One can hear such sound from a wine glass, as rarely a wine glass is perfectly round. If it is slightly elliptic, it has two very close resonance frequencies, and beat tone occurs. What we have just seen is the adding to two harmonic signals as a demonstration of the adder circuit. In the following, the adder is used to simulate the problem of noise and interference in communications. First, let's look at the message signal. It is a periodic repeat of a message that consists 14 bits, 1 and 0, representing two ASCII characters, H and I. For the sake of simplicity, we will not use any realistic transmission coding scheme, but represent the message with a simple two-level voltage modulation scheme. A pulse with high-level voltage for bit 1, and a pulse with zero voltage, that is, no pulse, for bit 0. The signal shown is actually the output from the adder circuit, hence it is inverted. The random pulse function of DG-Lent AD2 waveGen is used to simulate noise. One can vary the noise amplitude and frequency. In the follow, first, the message is shown without noise. Then noise is shown without message. And finally, message and noise are added to simulate a problem of typical noisy communication. Signal alone. Noise alone. Signal and noise added together. Can we tell where the signal is in the output? Or what it is? Since obviously, a message is sent only when the other end doesn't know what it is. No one sends a message that the receiving end already knows it. It looks hopeless, because it is. That is why there is communication engineering to solve such a problem. It is perhaps the biggest driver of electronics technology for more than a century, ever since the emergence of the vacuum tube. The transistor, the semiconductor integrated circuit, fiber optics, and photonics, quantum communications, all are driven by the human need of information sharing. It is the reason why circuits are taught in ECE curriculum. And the circuits in Lab 6 are both for learning about circuit theory, as well as for an appreciation of the role of electronics in communication technology.